Hello, my name is Kingsley Anton and welcome to this series on data structure and algorithm. In this video, I'm going to explain what linked list is, different types of linked lists, the advantage and disadvantage of linked list over arrays, the big O notation of linked lists, and the implementation of linked lists in Python. If you're a beginner, relax. I'm going to try my best to make this tutorial as simple as possible. Without further ado, let's dive into it. What is linked list? A linked list is a linear data structure that stores a collection of data elements dynamically in nodes. Linked list stores its values or data using nodes and connects these nodes with links. Now, linked list node contains two fields, the data field and the next. The data field contains the data or the value of the linked list, and the next contains the link or the reference to the next node. As we have on my screen, we have three nodes. The head node is the first node and the tail node is the last node. Now, this data field contains the value or the data of the linked list, the first data in the linked list, and the next, it contains the link that connects the head node to the next node, and the next node as well contains data of value in the data field, and next that contains the link or the reference to the next node. And this is how linked list connects from the head node down to the tail node. Also contains the data field and the next field. The next field contains the reference to the next node. Now, in the tail node, the next node is always null because there's no other node to connect or make reference to. Now, to better understand linked lists, let's understand how arrays are being stored in memories. Now, arrays are being stored in contiguous memory location. For example, we have my array equal to 2, 4, 6, 8, 9. So what Python does, not just Python, but every other programming language, what it does is it creates an initial capacity of 10 in our memory location to store this array and assign each value, each memory location in the memory space. Now we have 2, 4, 6, 8, 9. When our array grows from 5 values to 10, as we have in my array 2, Python add these added values to the remaining part of the memory location, as we have in the second diagram here. Now, the green part of this image signifies the memory location for other values, arrays, or variables. Like I said, arrays stores value in contiguous memory location, which means after allocating value for array, it goes ahead to allocate memory for another variable or another array continuously. So the blue part of this image is the part that houses or contains our value of our array, whereas the green part contains the value or is the memory location for another variable or array. So when our linked list grows beyond the initial capacity of 10, what Python does is it creates a new memory location and transfer these 10 values to the new memory location and add the added value in our array to the remaining part of the new memory location. Now, the way Python creates new array is it multiplies the initial capacity of 10 multiplied by 2, meaning it adds extra 10 space in our memory location to house this array. So now the array, the new memory location contains 20 boxes or 20 memory space to house our new array. Just like we explained, when this new array of 20 memory space is exceeded by maybe our array grows beyond 20 space or 20 values, which means the new memory location is occupied or filled. So Python will go ahead and create more location or more bigger memory space to house the new value added to our array. And how does Python do that? The same method. It multiplies the initial capacity of 20 multiplied by 2, making 40, and that is how it grows. And by doing this, it consumes a lot of time, and this is why array is not advisable or is not a good choice for large data size or inputs. And this is where LinkedIn come in play. So as we have on our screen here, we have an image of array and linked list. Now, just like I explained, array is being stored in contiguous memory location. So this is how array is being stored in memory space with its reference on the right and the index on the left. So when I try to fetch the value of 24, I make request by maybe print the name of the array. Let's say my array is square brackets index 0. It fetches 24 as my value. If I want to fetch the value of 80, I print array, that is the array name, my array in square brackets index of 3 to get my 80. So this is how array is being stored in memory location. So for linked lists are stored in scattered plots, and this is the advantage of linked list over arrays. Now linked list head can be in one location and the other node can be in the other location, and the tail can be in another location. So it can be scattered across our memory location. And to access any value from our linked list, we have to go through the head, because the head contains the reference or the link to the next node, and the next node contains the link to the next node. So there's no how we can access or go to the middle and access linked lists without going through the head. So we have to, or we must loop through the linked list from the beginning to the end. So linked list has its own advantage and disadvantage. So the advantage here is when we try to add more values in our linked list, it doesn't create a new memory location to add these values. It only change the reference of the previous node to the new node we're adding now, and assign the reference of the old node to the new node, which means it will place a value or node in between two values and change the reference to the new reference or the new node. So this is how linked lists work in Python. So let's go down to the types of linked lists. We have three types of linked lists: the singly linked list, doubly linked list, and circular linked lists. So the single linked list is the most common type of linked list. Each node has data and an address field that contains a reference to the next node, just like I explained. Now, the singly linked list is one directional, meaning it can only go forward and not backward. So it contains only two fields, the data field and the next field. Data field contains the value or the data of our linked list, and the next contains the reference or the link to the next node. The next node also contains two fields, the data field and the next. Data field contains the value or the data of this node, and the next field contains the reference or the link to the next node. And that is how it grows down to the tail. So the tail also contains two fields, the data field and the next field. So the data field contains the data or the value of the node. Then the next is null because there's no other node to make reference to. That is the tail. So this is where the singly linked list stops. After the tail, there's nothing to make reference to. Let's go down to the next, which is our doubly linked list. Now for a doubly linked list, the direction is bidirectional or two directional. It goes back and forth. So it contains three fields: the previous node, the data field, and the next node. So the previous contains the reference to the previous node, and the data contains the data or the value of the node, and the next contains the reference or the link to the next node. Likewise, the next node and the next node down to the tail. So then the tail node contains as well three fields: the previous, that is the reference or the link to the previous node before the tail node, the data field that contains the value or the data of this node, and the null, the next field contains null because there's no other reference or node to make reference to. So the next type of linked list is a circular linked list. From the word circular, it goes in one direction, then goes back to the head. So as you can see on our screen, we have two fields, the data field and the next. Data field contains the value or the data of this node, and the next contains the reference or the link to the next node, as well as the next node also contains data field and the next field. The data field contains value or data of this node, and the next node or the next field contains the reference or link to the next node. Then at the tail node also contains two fields, the data field and the next field. So the next field make reference to the head node. That is, the next field contains the reference to the starting of the linked list. So that is why it is called singular linked list. Understand the big O notation of arrays and linked lists. Now, the cost of accessing elements in array is constant time complexity. And why is it so? It's so because to actually access a value in our array, we just make requests or print the index of the value we're trying to access, right? But in linked list, we have to loop through the linked list by starting from the head down to the position where we want to fetch the value, right? Because in linked list, the head node contains the reference or the link to the next node, and the next node contains the link to the next node. So there's no how you can go to the middle of a linked list without going through or starting from the head nodes to loop through down to the value you're trying to fetch. So that is why array has a constant time complexity and linked list has a linear time complexity. So the next one is insert and remove from beginning. Now for array, to insert or remove value from an array has a linear time complexity, while in linked list it has a constant time complexity. I will explain this now. Let's go back to our image here. So the 2 here is the beginning of our array, right? And the 14 here is the end of our array. So in this case, when I try to remove the first value, now what Python does is Python will try to shift all these other values upward to take the space of the previous index. So assuming we have an array that contains millions of data values, this is how Python will shift them one after the other down to the last value. So this takes time. That is why we have a linear time complexity, right? Likewise, adding a value. So if we want to add a value, let's say we add a value to the beginning of our linked list, our already filled linked list, right? So what Python does is it shifts every other array downward and add the new value to the specified index. So every other index after it is moved downward. So this takes time, and Python moves them one after the other down to the last value. So that is why we have a linear time complexity for our array. Whereas in our linked lists, what Python does, not just Python, when I say Python, I mean every other programming language. Since I'm making this tutorial with Python, that's why I'm always saying Python, but it's applicable to other programming languages as well. So for linked list, if you're adding a value to the head node, we create a new node and assign it to the head, right? So the new node will now contain the next. So the next field of the new node will contain the link or the reference to the previous head. So the previous head now will become the next node, not the head again, right? So this is why we have a linear time complexity for our linked lists. So let's go down to insert, remove from the end. So in our array, when we try to remove a value from the end like this, Python does not move other values upward because that is the last value in our array. But in linked lists, we have to go through the array from the head, which is not really a good thing, because if we have a million or billion value in our linked list, Python have to loop through this million or billion values from the head down to the tail, then pull out the tail. So this take a linear time complexity. So the next one is insert or remove from the middle. So for both arrays and linked lists, they are both linear time complexity. And why is it so? It's so because in Python, if you try to either remove a value or insert a value at the middle of our array, the values before the removed or added value is either moved upward if we are removing or moved downward if you are adding. So assuming we have a million or billion values, now Python moves these values after the removed array either upward if you are removing and downward. So this takes time. So it's like looping through the array by shifting them downward to assign them the new index. Same applicable to linked lists. In linked lists, what Python does is it loops through to the end or the middle of our linked list and either inserts or remove. So the looping through from the head to the middle where we want to insert or remove a node takes a linear time complexity. So this is the difference between array and linked lists. Both of these data structures are applicable in different areas. Our values are of small size, we use array. But if it's of large size, we use linked list. So this is where linked list comes in play.